Hi. Hi, everyone. Good afternoon. Let's get started. It's 4 o'clock. And thank you for joining my talk about how we build our big data system. My name is Yoav, and I'm the Vice President of Engineering at Incapsula. Let's get started. I have a lot of things to tell you about today. So in this talk, I'm going to explain the different generations of software that we use to build our big data system. We have a lot of buzzwords here. So we use all of them, at least tried using all of them. And it's going to be very interesting. So a little bit about Incapsula to give you some context about what we do. So Incapsula is a leading vendor of a cloud-based application delivery controller. So what does that mean? It means that we give you all the services that you want running a web application on the internet. So web application firewall, load balancing, CDN, and best-of-breed DDoS protection. And how does Incapsula work? We place ourselves between your clients, the people trying to access your website, and the actual web servers. So we're in the middle, and we have our POPs, our points of presence, deployed around the world. And we see all the web traffic coming in. It's coming into our POP, and we filter out all the bad stuff. We let all the good stuff go through. We cache as much as possible. That's the basic idea. So in this talk, we're going to discuss web traffic. And we use a very simple model to describe the web traffic that we see on our service. So whenever I open a browser and I browse to some website, a session begins. And subsequent requests to that session in this browser window are associated to the same session. And if I close the window, I open another window, or if the session times out, then a new session is created, and the following request will be associated to the next request. It's a very simple model, and we use a session cookie on the browser to do the tracking. So we have dozens of POPs, almost 30 POPs around the world, from Tokyo to west of the United States. And each POP has between 3 and 10 edge servers, reverse proxy servers. And each proxy server reports a high throughput stream of messages that are encoded in Google protobuf format. And we have two types of messages. We have session messages and action messages. Session messages tell us when sessions begin and when they end. And action messages describe HTTP requests and responses. And so our problem for this talk, what we want to solve in this talk, is how do we take these hundreds and hundreds of high throughput streams that are created all around the world, and we bring them into one location and create data out of them that we can build features on top, like our reports and our dashboards. And while looking at the different solutions that we built over the years, I'm going to talk about, I'm going to measure them with three matrix or performance indicators. So one thing is the processing throughput. And for me, it means that we want to have as little time as possible from the moment the data is created on the edge server and until it's visible in the UI for the customer. We want to have a good read performance because we want people to log in and load the dashboards instantly and not wait for, I don't know, a few seconds to get them, or maybe more. And we want to have scalability with the solution. So for me, scalability means that if I throw in 10 times more data at the solution, it will still hold. Or, and that's OK too, I know what I have to do in order to make it work with 10 times more data. If I don't have either one, then I'm in serious trouble. I'm going to have a scalability breakdown very soon. So it's a bad place to be in. And this is always the question that we ask ourselves, whether this will work with 10 times more data. And the architecture that we have, this is something that hardly changed over the years. We have lots of POPs, and each POP writes these high throughput streams of data in basically files, one file per minute per edge server. And we upload these files into some data server where they are processed in some magical way and shoved into some database for our application to read. So this is the high-level context of what we do, and we have a different design in every generation. Okay, so let's get started with our first generation. Now, each generation has its pros and cons, and I'm going to cover them. I think that except the Gen 1, which only had cons to it. So I'll try to make this one simple because, as you can see, the solution, the design is not simple. So we have our POP server here, our POP and all the edge servers inside. And we use Amazon S3 as a mediator, as a buffer to store the files that are generated by the edge servers until they are picked up by our processing engine. So we encrypt the files, we upload them to S3, and from our processing server, we download them and we encrypt them. And after we have the files decrypted and downloaded on our processing server, we run them through a Java processor, and that Java processor takes those hundreds of thousands of messages, high throughput streams of messages, and processes them into CSV files. And those CSV files are then uploaded to a different server where they are inserted into the database, and we have a MySQL database on the database server. Now, this is very complex. And let's go over the data scheme that we had on the server. So this is your normal textbook solution. It's very generic. You can do a lot of stuff with it. It has its drawbacks, though. We'll cover them. So we have tables that map between certain dimensions and the counters, the metrics that we want to count. For example, we have a time dimension, and we have an IP address dimension, we have a country dimension, etc. So we have lots of dimensions. And we have the things that we want to count, which is number of HTTP requests, maybe number of sessions, number of attacks, stuff like that. And we take this table, and using SQL, we can answer any question that is possible within the domain of our dimensions. So I can write a query to count the number of attacks from Germany in a certain month. Now, you understand that as I add more dimensions, and the domain of each dimension could be very big, like an IP address, then the maximum number of rows in such a table is very, 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 very large. And being a very small company just starting up, without almost any customer, we reached tables of billions of rows. So this was very problematic for us. And in addition to having very big tables, if we wanted to load data, information about individual events, for example, here we have the post body of an attack, then we had to do joins between the session table and the actions table. So we didn't have a consistent, holistic view of a session the way you would expect that we will have. So very large tables, a generic solution, but poor performance. So we say that the processing speed was okay, but between you and me, we didn't have that many customers, and not the big customers that we have today. So it's an estimate. I think it was okay. It was better than the read performance, which was very, very bad, because we had to write an SQL query, to execute an SQL query for each chart that we wanted to display. And if we wanted to have a dashboard, a nice dashboard like we have today with 15 charts on the same page. We had to do 15 queries on a very large table, so that didn't work out quite well. And scalability-wise, well, since it got stuck with the amount of data that we currently had, so there's no point in trying to think about how it's going to scale with 10 times more data. And it was very, very complex because there were a lot of moving parts in the solution. You upload, and you download, and you encrypt, and you decrypt, and maybe S3 is not responding well, or you'd have to, basically debugging this system was very, very difficult. Lots of moving parts. So this brings us to the second generation. So in the second generation, which is codenamed, the first one I didn't mention was codenamed rtproc for real-time processor. So this is the next generation. And the main problems that we wanted to solve is to have a better read performance, because we had a very big problem with read. The dashboards would not load as fast as we wanted them to be. And we wanted something that is very, very simple. So instead of keeping the relational model that we had, the very big tables, we decided to minimize the requirements and go with a NoSQL model to improve our read performance. So we will not have joins, and we'll have very, well, not as big as tables as we had before. And in addition, we wanted to build our statistics not from the core data itself, not from the stream of session and action messages, because that is very costly. If we wanted to measure, let's say, the amount of bytes that are transferred through our network, then we had to report every HTTP request and that we processed, and that's lots of data. So requests to favicons and I don't know, some small images. There are many, many HTTP requests that are not very interesting to report on the individual level. So we decided not to report every HTTP request. We are reporting only interesting HTTP requests, but instead we count all the metrics that we need to count on the edge server, and we created a different message that only reports counters. So the number of bytes, number of HTTP requests, these are all counted on the edge and reported for aggregation. So the design looked like that. So each edge server in each POP reported two types of files. We now have events files, which are the original session and action streams, and we have stats files. Stats files are they contain this new type of message, the statistics message with just the counters in it. And these are uploaded into via Nginx as a file interface, a DAV interface on the server side, on the data server. These are uploaded to the data server, and they are streamed into two processing engines, which now we decided to write in Python. So it's very similar code for both of them. A few functions are different, of course. So we have a Python stats processor and an events processor. And for the database, we're now not using MySQL. We decided to use MongoDB because that was what we had around. That was the thing that was very easy to get started with. And our application server just connected to the database to get every information that we needed. So let's look at the schema that we had. I'm sorry, no schema. This is the schemaless database, but this is how the data looked like. So we gave up on keeping very generic data structures of tuples of dimensions to metrics. So we are just now keeping time series of data points. So for example, here we have the page views of the Incapsula.com website from September 4th. And as you can see, we have 12 data points. Each data point represents the number of page views that the number of page views of the site for a section of 2 hours in a day. So the read performance is a lot better now, because if I want to build a chart of the last 7 days or just 1 day, I only need to load as many objects as the number of days I need from the database. And each object contains all the data that I need to build all my charts. So I don't have to go back and forth to the database to build my charts. And in cases that I need it, I can always project the data and get only parts of the data from the database. It's a nice MongoDB feature. And it's a lot quicker if you need just bits of the data. And the events, the sessions NoSQL storage look like you would expect it to look like. So we have a session object, and the session object contains all the action objects within it. So for example, our security researchers can just look at a session and see the actions sequentially and understand what the hacker is trying to do, as opposed to before that they had to walk around, do some SQL queries. It would take time. It was complex. You wouldn't see it. You could not see it in a single object. So loading a single session is very easy. Just one object. You load it by its ID. And searches are OK. And what do I mean by searches? We have this user interface where you can type in, you can click on checkboxes. I want to see only attacks. I want to see traffic generated by a certain client type, for example, Internet Explorer. And I want to see traffic coming from China. And all of these filters are basically translated into MongoDB indexes. And we used MongoDB indexes for search. And it was OK. It wasn't great. It wasn't very fast. But at least it worked, and it worked OK. But we very quickly reached the point that we couldn't do much more with MongoDB indexes. But it was OK for the time. So the way our Python processor worked, and this was, the mindset was, let's keep it simple as much as possible. So we decided to do a batch process. So we have files which are uploaded, as you remember, and they sit in a directory on the file system, and we run the batch processor. Now, the batch processor runs for X minutes, say 5 minutes, processes as much files as it can, and once there are no more files or it reaches its time limit, it flushes everything to the database and exits and starts again, maybe a minute or two afterwards. So this is very, very simple. Now, since it's a batch process, we don't have any context in between runs. We lose the entire context. And this is a bit of a problem. We'll talk about it later on. But in a single run, we cache all the objects that we work on. So, for example, if I get an update for some session, I load it the first time from the database. I update it. I put it in the cache of the process. And later on, if I get another update for this session, I don't have to look it up from the database again. And when the entire process ends, I flush all the sessions from all the data from the cache to the database. So this worked fine. It worked fine as a proof of concept, and it started working fine in production for the first few weeks. And after a few weeks, we started to run into some problems with the database. And we had lots of problems. For example, if we wanted to change one of the indices, it would take forever, and it wasn't that big of a database at that time. And the main problem that we had is that we designed just one database for all the sessions of all the sites of all of our customers. And this database was starting to get big, and we started getting into some trouble. And MongoDB has not a great concurrency features into it. I would say this mildly. And it has one lock, or at least at the time, it had one lock per database server. So if you do a write, you can't do a read in the entire database server. So that's a very big problem because our batch process likes to do lots of writes in a short period of time, which as the amount of data gets bigger, this time frame becomes larger. And also, the lock has preference for writers. So if I have readers waiting and I have a writer coming in, then it's going to block all the readers. And if you think about it, the other way around sucks just as much. So it just depends on who you want to block. So we had a problem with locking, which was a very big problem because people were trying to access the dashboard and they couldn't get the data they wanted because the batch process was flushing data. And if they waited a minute, it was fine, it was very fast. But we couldn't rely on this, we couldn't continue with this situation. Dropping all data was practically impossible because we had to go over all the objects, all the sessions, for each one of them, check if they're old enough, for example, older than 90 days, and delete them. In addition, deletions in MongoDB do not reclaim disk space. You have to compact the database, which makes perfect sense, okay? It makes perfect sense, but it's a problem. And if you don't know that in advance, it's a very big problem, and you're already in production, and it's a problem. And also fragmentation was a big problem for us, because when if you look at the lifetime of a session, so it starts very small, just, I don't know, 10, 20, 30 bytes, but then it gets accumulated with actions and more actions, and the session gets bigger, and sessions can get up to 1 kilobyte, and maybe even more if we store post body of HTTP requests, and we do. And fragmentation was a really big issue, and if you add that to the deletions that don't reclaim disk space, we were running out of disk space all the time. It was a very big problem, lots of sleepless nights. So we had to do something about it. And we decided to refactor the way we work with MongoDB. So instead of just one database, now we keep a single database for each day. So there's a database for all the sessions that started today. There's a database for all the sessions that started yesterday. Now, this is great because we can drop old databases very quickly, and it's very, very simple, so it solves problem number one. And fragmentation is also kind of solved very elegantly, I must say, because we know when a session is still accumulating data, we call it live session, and we know when a session ends, we call this a dead session. So when a session ends, when we get a report that a session ends, we take it and we place it in the per day DB. Until it's placed in the per day DB, it's stored in what we call the live sessions database, which is a dump. It's completely fragmented. It's a very big problem in itself, but it's contained. So we were able to contain a fragmentation problem to just one single database, which is not very big. And all the other databases, so 99% of our storage is now unfragmented, which is very, very good. And we had to do some maintenance to keep the live partitions in check. So we had a daily process every morning. We have a scheduled process that would go over the live sessions, would delete every session that should have been deleted, move it to the per day DB, compact the database, and we're good to go. And it was okay. It was tolerable. It was fine for the time. Well, DB locking was still a problem. And again, there's no good solution to that, but we were able to contain the problem by running 2 MongoDB instances side by side on the same server, just so that the global lock will not interfere. So we had one database instance for stats, which are usually quite efficient. The flush time is very, very short. And we had one database instance for events, which the flush time is longer, but it's more tolerable because the worst thing that you can expect is that someone is trying to access a dashboard and the dashboard doesn't load like that. So if someone is doing a search to find specific events, I think that people are more tolerable in that use case. So I think now MongoDB has better locking, but I'm not keeping track anymore. So let's analyze Gen 2. It was very simple. It was very simple. This is one of the reasons that we decided to use Python. We wanted to make it as simplest as possible. We wanted to be able to change code at runtime, to make it very, very lean. MongoDB was very easy to get started with and was very easy to get into roadblocks with. And over time, TCO increases, which is a nice way to saying that we had a very hard time with it. And as I said before, lots of sleepless nights. And we kind of feel that we reached the limits of doing this process in batch, because the flush time at the end of the batch was beginning to become very, very large, long. We would process files for 5 minutes, and we would flush to the database for 5 minutes. And that doesn't seem like a good place to be. So processing-wise, it was OK. It was a lot better than we had before. Read performance was OK after we solved all the problems. And scalability-wise, it was OK because it definitely qualified as being able to process 10 times more data. And actually, we started off having 1 stats and 1 events processor. And we ended up having 1 stats and 6 events processors. So we could add more processes as needed, but eventually the database becomes the bottleneck, and we could have expanded the database, started using sharding, etc. But we were so we decided we're not going to continue investing in Mongo at that time. So we wanted a different solution. So we started working on the next generation. So the next generation was codenamed Graceland, and the main problems that we wanted to solve is we wanted faster online processing, and online processing means that the process is not working in batch. It's not started working we're not starting it working for a few minutes and then it ends. It's alive all the time. It's up for months, and we don't have to take it down. And we don't have concentrated flush times where we put lots of objects from memory to the database. We wanted to have better search capabilities because we wanted to give our users the option to search, to do text searches, to search all URLs that were used for SQL injection that contain a certain keyword, for example. And we couldn't do that with MongoDB. And also our security researchers needed that capability, and they are one of the drivers of all the developments that we do. So the new approach was this. We're going to go back to Java because we want to have to use a faster protobuf library than we have in Python. We wanted a process that could be alive for an infinite amount of time, and we wanted to reduce the time it takes to flush objects to storage. At this point, we understood we have done a few proof of concepts with Lucene as a search engine, and we understood that we wanted Lucene, and this is another reason that we went back to Java. And we wanted a database that you don't have to become a DBA or hire a DBA to be able to operate in production. Because even in Gen 1 with the MySQL, we had a DBA that we hired, and once in a while, the database crashed, and these were my ISM tables, and nothing worked, and we had to call the DBA in the middle of the night, and he would log in, he would do some repair command, and it will take some time, and everything was okay. So we wanted something that we could control, that nothing would be a black box to us. We can understand everything. Okay. So the design is very similar to what we had in Gen 2, but we just replaced some of the components. So we still have event stream, we still have stat stream, we still upload data into data servers using Nginx as an interface for Dove. This time we have separate servers, but it doesn't really matter, just an implementation issue or a detail. And we have different storages for each type of data. We have what we call a segmented storage file system for stats, and we have a session store and the Lucene index for the sessions. And I'm going to explain more about it in a few minutes, but there's a really weird line between our web application, as you can see, and it doesn't go into the database. So the web application does not actually interact with the database. It interacts with the data via Nginx. And this is one of the coolest things that we did, is that all the data, both for stats and for events, are just static files. And we can just access them via Nginx, and that's super scalable and very simple to do. So I'm going to expand more about it in a second. So the multi-threaded Java processor looks like this. It has two types of threads, one reader thread and one worker thread. The job of the reader thread is to read the files and load balance all the messages in the files to all the worker threads. And the job of the worker thread is to actually process the message. And by processing the message, I mean read the message, take the object from cache, run the code that updates the object in the cache, and take the next message. And when time comes, for example, when a session ends, take the session, remove it from the cache, and put it in storage. Okay, so the segmented storage file system, which is our database for statistics, is basically 4 or 5 files, depends on the configuration, per site. And by site, I mean www.incapsula.com, that's a site on the service. my.incapsula.com, that's another site on the service, and we have lots and lots of sites. So we have 4 or 5 files per site, and we have 2 types of files. We have an independent file, which is just, file in the file system. We have a big file that is called the archive file, and we have an index file. So what's the idea here? We have lots and lots of sites on the service, and each file contains all the data, all the statistical data for a single day. Now, if you multiply the amounts of days that sites are on the service, and that's a lot, we have sites that are years and years on the service, and the number of sites that we have, which is a lot, you can get to billions of files. And we wanted to keep the number of files in the file system in check. So we decided to keep recent files outside of the archive and older files inside the archive. And we have the index file to tell us where to look for the data. So the index file is basically a simple table. We have the date that we want to know where the data is. We have the file name where the data is located. And if it's an individual file, if the day, let's say I'm trying to fetch yesterday's data, then probably this is an individual file, standalone file. So the data is from offset 0. But if it's an older day, then it's probably already compacted into the archive file, and we have the offset written. And we know the offset and the length to read from the big archive file to find the data that we need. And of course, whenever a new day comes in, we create a new independent file, and we archive the oldest independent file that we have. And the cool thing about it is that all the files are static files, simple files that we can access using HTTP with Nginx, and it's super scalable, at least for our needs. And whenever a user comes in and goes into the dashboard and tries to see all the charts for his or her site, then we send an HTTP request from our application server to Nginx, and we request the index file. So we take the index file, which is binary, it's very, very, very small amount of bytes. We take the index file, we parse it, and we understand which files or file segments we need to fetch from the data server, and we issue the HTTP request that we need in order to get the data. We do it asynchronously in parallel, so it's very fast. And in addition, once we get all the files in the application server, we just store them in the file system with the index file. So if tomorrow the same user logs in and tries to see the dashboard, all we need to do is now update just one file, the file for this new day. And it's super fast. We just load the files, read them, build the data points we need for the charts, send them to the client side, and it's super fast and super simple, which we like. So for the events storage, we tried different approaches. Basically, what we needed is just a simple key value store, nothing fancy, because we decided that we're going to use Lucene for all the searches, so we just need to load by ID. And we tried different approaches. The first attempt that we had was just to use Lucene itself, the index itself, to store the data of the session. And in Lucene, you can take a field and say, hey, Lucene, this is a binary field. I'm going to give you this byte array. Just store this byte array in the index as is. And this didn't work out very well because the raw session data was mixed with the index data and some fields that we actually had to load while we do the search. And all the thing got memory mapped, and it was very it was very memory hungry, I would say. So that wasn't a great solution. It was simple in proof of concept, but it didn't make it to production. We tried some simple key value stores like LevelDB or Kyoto Cabinet. We couldn't get them to work reliably in Java. Honestly, we didn't try as much to get them to work. And we also tried to use Cassandra. And this was, I gave a talk, an internal talk in the company about 2 years ago, and I was saying, hey, we're going to try use Cassandra. I was very happy about it. And we took one of the sysadmins and we told him, hey, now you have to learn Cassandra, and you have to be a Cassandra master. And we set up all these Amazon instances all over the world to test the cross-data center replication, et cetera. And actually, what we felt is that it was too complicated for what we needed to do with it. Just be a simple key value store, maybe give us some reliability. So Cassandra didn't make it to production. And probably we needed someone who understood Cassandra better. And so that would be awesome if we had someone who knew Cassandra very, very well. But on the other hand, if we had someone who knew Cassandra very, very well, we'd be using Cassandra in production today. And I don't know if that's a good thing or not, because I think that we can do it better for what we need. So the event store, the session store, became a very, very simple key value store. The way we like it, we like to use files. So we have a directory in the file system for each day, and this directory has two subdirectories, one holding the Lucene index, as is Lucene, simple Lucene index, and the other one is holding just a bunch of files. Each file is 2 gigs long, or 2 gigs big, I'm sorry, and all the sessions are just appended into this big file, and we have our index to tell us how to load, where is the session located. So we can just, again, use Nginx and go and fetch exactly the amounts of bytes that we want using the range header in HTTP, because we know where the session is located in the data. We have the file name, we have the offset, and we have the length. And again, we use the same approach for live sessions and dead sessions. So we have 0 fragmentation in the per day partitions. We have fragmentation issues in the live partitions. And we have the same methodology as we had before to handle that. So searches I think are really, really cool right now because we do a search request, and the user is typing everything that they wanted to search for. They type the IP address or the type of attack and the type of client, whatever they want. And now we have very good search capabilities, and we send the search request from our application server to the data server. And we send it, and we search the index, and the search is very, very fast. We get what we call a session summary object back. So on the index itself, on each document, we store enough data, enough raw, readable data, in order to build a session summary, which is this top section with the tags on it and all these little bits of information. So this is built right from the index. And only when the user clicks on more, then we issue an HTTP request from our application server to the data server via Nginx to fetch exactly this and that amount of bytes from this specific file. And we get the data, we decompress it because everything in the storage is deflated. So we inflate the data and send it to the client, and it's actually very, very fast. It's way below 1 second to do that. And the searches themselves most of them are below 1 second. So to analyze the 3rd generation, I would say that we have a pretty good processing throughput. I can give you some numbers. We can reach about 40 megabytes per second of data, of raw data that we process, which is a lot more than we could do before. I think that before in Gen 2, we reached about 6 megabytes per second. So now we have 40. We have very good read performance. The stats are just flying in, and all the searches for individual events are flying in, and we have more search features, which is a great thing. However, we are reaching some JVM issues because as you remember, we have lots of worker threads, and each worker thread has its own cache. And these caches take up lots of memory. So right now, we're running in production with heap size of about 20 to 50 gigs. And it's OK. We're not suffering very much from garbage collection. But again, the JVM commits lots of memory from the system. And we are working on ways to run with lower memory footprint. And one of the things that we do is our caches are layered. It means that only a small percentage of the cache is actually in the JVM heap space. All the other stuff, something like 20% is in the 20% of the cache size is in the JVM heap space, and the other 80 we store somewhere else. So we tried Redis for that. We couldn't get as much throughput as we wanted out of it. We tried to store each session as an individual file the way we like. That was OK. It was pretty fast, but we ended up with lots of files, lots of small files. And as you know, small files in a standard format of a file system may become very costly because they take up all the inodes. Eventually, the way we like it, we have just a very big file to keep all the sessions inside, and we have an index in memory to tell us where the sessions are. So it's pretty efficient. It's a good design. And to give you an overall score of the solution, I think that processing-wise, we're good. We're doing 40 megs per second on a single node, which is OK. Read performance is very good. We don't have any blocks, don't have any issues with reading. And scalability-wise, it's very scalable because we can take a bigger machine with more cores and more RAM and run it. I haven't tried committing a 200 gig JVM heap space, but that's a could be a cool experiment to do to see how big can we get before collapsing. And overall, we're very happy with this solution. This is what we are running now in production. So before I finish my talk, I'm just going to give you some hints about what we're going to do for next year. And we're probably going to call that Gen 4. And so we're quite happy with what we have today in Gen 3, the multi-threaded Java process. Everything is very organized, and we have a good understanding of the trade-offs of the system. We don't have any black box database that we don't know nothing about and that we have to learn if we want to master our system. So we're going to use Gen 3, but instead of uploading all the data from Tokyo to the United States, from Europe to the United States, etc., which is becoming quite it could become quite a problem. It's not a problem at the moment, but I would expect it to become a problem next year because right now we're uploading about 1 terabyte a day. So 10 terabytes a day, that sounds problematic to me. So what we're going to do is we're going to run a data server on each POP. So next year we're going to have 30 POPs. We're going to have 30 data servers, which is a lot, which is great. And each data server in each POP will get the files of the edge servers in that POP, and will process and store all the data of this POP. And that's great. And now we just have to decide whether we upload some information into a central search server in order to facilitate searching, or do we do distributed search? So we can send a search request to 30 POPs and get all the results back and aggregate them. We haven't decided about that, but this is what we're working on right now. This is what we're thinking of. And yeah, interesting times ahead. So to summarize our experience, so we started as a very small company, very limited amount of resources. We didn't have the money to buy very big systems to host very big databases. And these are our takeaways. So we think it's equally important especially for a tech company, to understand every bit of technology that it's using, as it is important for it to understand every other aspect of the company, the sales cycle, the support cycle, etc. So for a tech company, this is the bread and butter. This is the technology. We have to understand everything. And we kind of reached the point where we prefer to write our own software than to use some black box solutions. But bear in mind, we do use libraries, of course. We are using Lucene, which is working great for us. But we're probably not going to use Solr because, to me, that's a black box solution. I'd rather use Lucene and embed Lucene and not use just this monolithic server that I don't understand and maybe have some feature that I don't need. And so everything I showed you in Gen 3 is pretty much very simple for every software developer to write. Write and read from files, nothing very complicated, do some HTTP requests. So we don't have to recruit people based on their knowledge in a specific field. So it's not like we sit together and we decide, hey, Cassandra, that's the thing to do. And OK, so we don't know anything about Cassandra. In order to make it work, we need to find someone who knows Cassandra. So A, it's a problem. Maybe could be a problem to find someone who knows Cassandra. B, once you get someone who knows Cassandra, you're going to run Cassandra because this guy wants you to run Cassandra. So I think it affects the overall decision-making processes when you have people who are very invested in a specific technology. Usually for a startup company, you have less requirements early on than you have later on. And of course, now that we have big customers, we have big and difficult requirements, but we understand our system and we know how to implement that, and we can add features as we go along. We don't have to pay the overhead of multi-DC replication or data encryption at rest or things like that when we're just a small company with a limited number of customers. And at the end of the day, I think that our journey reflects the DNA of the company. So we're an engineering company. That's our DNA. We love to write our own code. And it gives us, we prefer to write our own code than to look for Stack Overflows or crawl support or read documentation. So we can control everything. And if we have some problems, we can always hack it in the middle of the night, and we have done so to deal with various events that occurred during these years. And for a tech company, I think this is the way to go. And actually, for us, it was way more fun to do it that way. So thank you. I'll be taking your questions now. Yeah.
So with each iteration, it gets simpler, right? So how did you resist and probably a good effect for you, how did you resist the urge to overcome?
So the question was.
Please repeat the question.
Yeah, I'm repeating. So the question was, with each iteration, it became simpler, and how we resisted the urge to overcomplicate. I think it was a challenge, and you can see the Cassandra example, which is a good example to that. So we were starting a new version of the software, and I was saying, hey, let's use Cassandra. I'm reading all these blogs about Cassandra, and it's great, etc. But you really have to be honest with yourself, and what is important to me, what is important right now, what features I can delay to later time. Maybe I can do encryption at rest next year. Maybe I don't need it right now. And just think about the simplest possible way you can do that. So it requires some thinking, some self-control, and a humility to come and say, well, this is not working great as I expected, and I need to rethink it. Yes? It's a good question. The question was whether we are worried that building our own software is going to impact the velocity of the company moving forward. And I think it can impact the velocity of a company because, sure, if you know the technologies that you're using, you know them very well. If we had a MongoDB expert when we built our system, we probably would not have to overcome all the challenges that we had. But that said, being a technology company, technology is our business. And we need to be at the level that we understand every line of code, every consideration. And I'm not sure it's very easy to reach that level of knowledge using black box solutions. And again, we use solutions, we use some libraries, but we probably are not using them as black boxes.
Kind of follow up there. With looking at something like Apache Kafka or Presto, those two solutions are essentially similar pipelines. Why not be active in the community and actually commit to those and say hey, we're going to stand behind this and actually make a commitment to open source behind it?
It's a good question. The question was, why not stand behind open source projects and be active and commit to those projects and influence them? I think that we may do that in the future. I'm not overruling that completely. But if you mentioned velocity, then the one thing that using open source can probably harm you is that you are dependent of the community to provide you with features. Now, you see all these tech companies that are writing blogs again. Hey, we are now supporting this and that feature. Hey, we're going to make the internet better, and we are now supporting this and that. Well, I don't know if this and that was developed in this tech company or just a new release of some open source came up and some master's student decided to implement some feature. So now you get it, and then you can tell that you have it. So I always think that for a tech company, if you look at real technology companies, you see that they build most of their software. Yes?
How do you deal with the single points of failure?
Okay, so the question was how do we cope with single points of failure with the solution? We try to identify where we can break down, and we address it case by case. For example, we have a replication going on between our data servers, and we do that using our own, of course, solution because the data model is our own. We have fallback data servers that we can start uploading files to those if the master data servers are crashing or inaccessible, etc. So we tailor a solution to each problem, different problems.
I thought you described that you have a single Java process in which one data runs.
Yes, but we have more than one data server that runs this Java process. And we have replication going on between a master data server and a slave data server. And if in the occasion that the master data server is inaccessible, we can start uploading files to the slave data server, and it has a replication of the data, so we can just move on and read and write from that data server. So it's more of we kind of clone the application, and we do the fault tolerant relatively high up the stack. So we're not using a replication on the file system level or things like that. So we do it more in the application layer. Yes?
I assume the Java process don't have a name or didn't give a name for basically is doing fairly simple file management. Could you give more detail on it?
I'd love to. The name of the Java process is Graceland, just because the first machine when we started testing it was named Elvis. And I don't know why it was named Elvis, but so it popped Graceland, the name, and it stuck. So this Java process, what it does is it has a directory where it has all the files that it needs to process. Maybe I'll take us to that slide quickly. Yes. So Nginx gets all the files, and it puts them in some file system directory. We call this the inbox directory. And the inbox directory just contains a bunch of files that the system needs to process. And we have a reader thread that is working in loops. And each loop of the reader thread, it checks how many files it has in the inbox directory and starts going over the files in order of their creation. And it reads the files, and the files are just contain messages in binary format. We use Google Protobuf to encode the messages. And so we read message by message. And once we read the message, we know to which site the message belongs to. So each site has a unique identifier generated by our database. So then we take the message and we put it in a different file, in a different directory, which we call the worker inbox directory. And we load balance just by moduling the site ID with the number of processes that we have. So very simple. If we have 10 processes and we have site number 7, then we know exactly to which worker it belongs. So we put all the messages in a different file, and then the worker thread, which also runs in loops, starts its iteration, see that it has this and that amount of files, and now it reads the messages from the file and loads the object from cache. Let's say, for example, that we have a new HTTP request to report. So we have an action message, and action is always embedded inside a session. So the action message contains the ID of the session that we need to update. So we load the session from cache. We take the action and the session, we combine them together. It's a simple data structure and a few lines of code to actually update that. And we put the session back in the cache. So the next action that comes along, we'll do the same thing. So if now we have this session object in cache, and now comes along a session termination message, which tells us that this session is not going to be updated anymore. So after updating this information onto the session, we take it, we append it to the value store file, which is a big 2 gig file. We just append it to the end of the file, and we know what is the offset in the file and how many bytes this session consumes, and we take that information and we index it in the Lucene index. So the Lucene index contains the file name, the offset in the file, and the amount of bytes that we need to load in order to read the raw session information.
I have a follow-up.
Sure.
So, you mentioned JVM heap issues. Have you considered going to C++ where you can control your own memory and more direct control?
Yes, we have, and we're not a very C++ shop company. We're more of a C company because all the edge servers are, again, we wrote them ourselves in C. Same thing, yes. I think that one of the challenges that we'll have moving to C is that we are pretty happy with Lucene as an indexing and search engine. So I'm not fairly sure that there's an implementation of Lucene for C. I know there's an implementation in Python. But I think that we can also tune our applications to run OK and not reach JVM issues. OK, so we're out of time. I'm here if you want to ask more questions. Thank you very much. Thank you for your questions. I had a great time.